In lab, you guys were looking at the period of a pendulum and how it was affected by length, gravity, amplitude, and we noticed that as long as the amplitude was small, less than 1 radian, then the angle didn't really affect it. It was only the length that affected the period of a pendulum. In fact, we came up with the equation that omega is equal to the square root of g over L. Now, I always remember this because I think, okay, if gravity's bigger, it's got a stronger force pulling it, so it should go faster, so g's on top. The longer it is, the greater its moment of inertia, so that's going to decrease how often it swings, so L's on bottom. And then to convert that to frequency, remember frequency, this is angular frequency, and there are 2 pi radians per complete cycle, and so I got to take this radians divided by 2 pi in order to get to frequency. So 1 over 2 pi times the square root of g over L. And then finally, period, which is the time for one complete swing, which is the inverse of frequency, is just 2 pi times the square root of L over g, where L is the length of the pendulum and g is the acceleration due to gravity. So first question, how long is a pendulum if t equals 1 second? Well, we're going to put in 1 for t. We leave 2 pi over here, square root L over g. Alright, and I'm solving for L, and I know g, because we're on Earth, g equals 9.8 meters per second per second. So first thing to do is probably divide by 2 pi. So now I have 1 over 2 pi equals the square root of L over g. Now I want to square both sides, so square this side, square that side, and that gets me 1 over 4 pi squared equals L over g. Multiply both sides by g, or 9.8 divided by 4 pi squared equals L. And this gets me a length 9.8 divided by 4 pi squared. Now remember to put that pi square in parentheses, or it will divide by 4 and multiplied by pi. L equals 0.248 meters.